Going underground on Mars solves the radiation problem and creates a new one. The ground itself is the weapon, and InSight spent 4 years measuring how often it fires. You dig down to escape the invisible killer above you. You build walls, seal the tunnels, breathe recycled air, and for a few months, it works. Then the ground moves, and the thing that was saving your life starts to bury you. And that's not even the part nobody anticipated. The part nobody anticipated is why going deeper makes it worse, not better. Stand on the surface of Mars for 1 unshielded year, and you absorb 5 times more radiation than a person living on Earth. Enough that your bone marrow begins accumulating damage faster than it can repair itself. Do it for 5 years, and your cancer risk doubles. Do it for 10, and it quadruples. The surface is not a place where humans can stay. That's not speculation. That's the calculation that ends every Mars survival plan at the same sentence: go underground. Everyone agrees. The physics is obvious. The solution seems clean. What nobody talks about is what the ground is made of. The Mars surface is covered in a layer of loose, dusty, broken-up material called regolith. Think of it as the skin of the planet. It looks like soil. It behaves nothing like soil. Soil on Earth is compacted, mineral-dense, held together by moisture and organic material. Mars regolith is closer to a pile of marbles loosely stacked in a bag. More than half of it, by volume, is empty air pockets. Imagine building your home not in packed clay, but in compacted foam. That foam is the material between you and the radiation above. That foam is also the material that shakes when the planet moves. And Mars moves. Before NASA's InSight lander landed in November 2018, nobody knew how often. InSight was a seismic station, a device designed specifically to listen to the planet from the inside. What it recorded over the following 4 years was not a quiet, geologically dead world. It detected over 1,300 Marsquakes before its mission ended in December 2022. That's not once a week. That averages to almost once per day. In May 2022, it recorded the largest seismic event ever measured on another planet. A quake strong enough that, on Earth, it would topple unsecured equipment, crack concrete structures, and send emergency alerts across a region. The ground that was keeping you safe from radiation had been shaking beneath your tunnel every single day. You just didn't know it yet. Here's what nobody told you about Martian quakes. They're not caused by tectonic plates grinding against each other the way Earth's earthquakes are. Mars has no tectonic plates. Its quakes come from the planet cooling and slowly contracting, cracking itself from the inside as it shrinks. That sounds less violent. It isn't. The energy still travels through the ground, and the ground it travels through is that same loose, porous, hollow-pocketed regolith. When seismic energy moves through material like that, something happens that engineers on Earth have measured in earthquake zones. Soft ground amplifies shaking rather than absorbing it. The vibrations bounce around inside the loose structure, held longer, felt harder at the surface. The deeper you go into this material, the more of it surrounds you, and the more of it can move. Picture the moment it starts. You are 3 months into a 6-month rotation, 20 meters underground in a pressurized tunnel. Your habitat connects to a sealed airlock at one end and a laboratory module at the other. The tunnel walls are reinforced with anchored panels. The air recyclers are running. Everything is nominal. Then, the first tremor hits. It doesn't feel dramatic at first. A low vibration through the floor, a faint hum through the walls. You felt minor tremors before. You know the planet moves. What you don't feel, yet, is what's happening in the regolith around the tunnel wall. the loose granular material is starting to shift. Individual particles, separated by air gaps, are beginning to slide past each other, the same way a bag of marbles rearranges when you shake it. The structure isn't crumbling yet, but the material supporting your tunnel walls from the outside is no longer in the same configuration it was 30 seconds ago. The regolith around the tunnel wall loses its arrangement. The panel anchors, which were designed for static pressure from stable ground, are now receiving pressure from ground that is moving in multiple directions at once. Anchors designed for a push are now experiencing twisting. 2 anchor bolts on the eastern wall section fail, not catastrophically, not with a bang. They simply pull free of material that no longer grips them. The panel shifts inward 4 centimeters. A hairline crack opens in the pressure seal where the panel meets the tunnel ceiling junction. The crack is small, 2 millimeters wide. The pressure inside your tunnel is higher than the near vacuum outside. Air begins moving through the gap, slowly at first, then faster as the pressure differential widens the crack. You hear it before you see it, a faint hiss, the kind that means the boundary between you and the Martian atmosphere is no longer sealed. The outside atmosphere is roughly 1% of normal air pressure, cold enough to freeze gasoline, with almost no oxygen. Your suit is not on. Your suit is in a locker at the far end of the connecting module, 40 meters away. The regolith above the cracked panel section, now unsupported from below, begins to slump. This is the piece nobody models cleanly in tunnel simulations. Loose material doesn't fall all at once. It flows, slowly, silently, like sand through a crack in a container. The slumping material adds downward pressure on the already compromised panel. The crack widens. The hiss becomes audible from across the module. Your pressure alarm sounds. You have lost 12% of cabin pressure in 40 seconds. You have your suit in a locker 40 meters away and a tunnel section between you and it that may have partial blockage from shifted soil. The slumping reaches a volume where the panel fails entirely. The section collapses inward. The pressure equalization is now no longer a slow leak, it's a rupture. You have between 15 and 20 seconds of useful consciousness in the pressure drop that follows. Your body will keep moving for a few more seconds after your vision narrows. You will not reach your suit in 15 seconds from 40 meters through a partially collapsed connecting section, with shaking ground still active beneath your feet. The exit tunnel to the surface is behind you, and the surface above is the radiation field you came underground to escape. Physics has not given you a third option. You are choosing, in the final seconds of useful thought, between 2 deaths, and the planet decides the timing. The obvious answer is build deeper and reinforce the walls more heavily. If loose regolith near the surface is unstable, dig further down where the shaking is weaker. Add thicker wall panels. Use more anchor bolts. Apply enough engineering force to the problem and the geology stops mattering. The first part of that thinking is correct. Deeper locations do experience somewhat less shaking from surface disturbances. That part of the logic holds. What it misses is everything that happens to the material between the surface and your tunnel as you go further down. Regolith doesn't change its character with depth. It remains loose, porous, granular material. The same bag of marbles structure for the first several meters. When a seismic wave travels upward through that material toward the surface, it moves through progressively looser, less dense ground. That transition amplifies the wave rather than dampening it. Engineers studying earthquake damage on Earth have mapped this for decades in coastal cities built on sandy soil. The same seismic event causes dramatically more damage in areas of loose sediment than in areas of bedrock. The term for this is site amplification. The soft ground acts like a resonator, holding the vibration longer, bouncing it between particles. delivering a stronger and longer shake to anything built within it. The InSight data showed that the near-surface layer of Mars behaves exactly this way. The planet's loose outer layer holds seismic vibrations longer than bedrock would. The same wave that might pass through solid rock in seconds bounces through regolith for minutes. Going deeper doesn't put you below this effect. It puts more of the amplifying material above you. And here is the part that defeats the engineering solution entirely. Reinforcing your walls doesn't fix the foundation. You can make your wall panels thicker, you can use stronger anchors, but those anchors are still embedded in loose regolith. The structure can be perfect, the ground around it is still a bag of marbles. When the marbles shift, your perfect anchors shift with them. Reinforcement is an answer to static pressure. It is not an answer to a foundation that liquefies and rearranges itself. Every additional meter of depth you add to escape radiation is another meter of unstable material that can move above you, around you, and between you and the surface. More depth doesn't reduce the trap, it deepens it. May 4th, 2022. InSight Lander, Elysium Planitia, Mars. The lander had been sitting on the Martian surface for 3.5 years, listening. Its seismometer, a device sensitive enough to detect ground movements smaller than the width of a hydrogen atom, had been recording steadily since landing. The science team at the Jet Propulsion Laboratory in California had reviewed hundreds of smaller events. They had a general profile of what Martian seismic activity looked like. Then, the readings on May 4th came through. The event registered at what seismologists classified as equivalent to a Strength 5 quake on Earth. That number needs context. A Strength 5 quake on Earth is the threshold at which structural damage to buildings becomes likely. Unsecured shelving falls, masonry cracks, older structures fail. It is strong enough to be felt as violent shaking by anyone inside a building. It is the kind of event that triggers emergency response protocols in populated areas. The InSight team knew immediately what the data meant. The lander had just recorded the largest seismic event ever measured on any planet other than Earth. The quake was not caused by tectonic plates. Mars has none. It was caused by the planet cracking as it cooled, a structural failure occurring thousands of kilometers below the surface in the deep interior of a body that had been slowly contracting for billions of years. Nobody could predict it. Nobody could prevent it. The planet simply decided to crack, and the surface shook for what InSight sensors showed was a remarkably long duration. Longer than most earthquakes of comparable size, because the Martian crust transmits energy differently. What the science team also noted, InSight itself survived because it was sitting on the surface, not built into it. No pressurized walls, no anchor bolts in regolith, no sealed tunnel to rupture. The lander had no habitat, no crew, no exit problem. The data it transmitted was the exact warning that a human crew underground during that same event would not have been able to send afterward. The instrument survived to describe the event precisely because it had no infrastructure to destroy. That gap between what the data shows and what it means for a pressurized habitat is the gap that no human Mars mission has yet crossed. The record stands. The physics it documented has not changed. There is a version of this story where the problem has a clean solution. Engineers have proposed it: lava tubes. Billions of years ago, Mars had active volcanoes. When lava flowed and the outer surface cooled and hardened, the molten material inside kept moving, eventually draining out and leaving behind hollow tubes of solid basalt. Natural underground caves with walls that are not loose regolith, but rigid rock. Those walls don't liquefy. They were stress-tested by geological forces far larger than any Marsquake InSight recorded. They exist.
Satellite data suggests some of them are large enough to fit a city inside.
But they haven't been mapped with sufficient detail to identify structurally sound candidates. They haven't been physically surveyed. Their internal atmospheres, their floor stability, their accessibility from the surface, none of it has been verified. They represent a geological inheritance that Mars may have left precisely where humans could use it. Or not. The data doesn't say yet. The honest answer from the InSight mission is this. The underground base is not a solved problem with a construction timeline. It is an engineering problem with no signed-off answer. You are not choosing between danger and safety on Mars. You are choosing which mechanism the planet uses to kill you and how fast. The radiation above is patient. The ground below is not. The safest place on Mars and the most dangerous place on Mars are the same coordinates. And for 4 years, a small seismic lander sat on the surface, recording proof of exactly how often that remains true.